The other large group of Brownstein-Lowry weak bases consists of the anions of weak acids. And those anions of weak acids are going to function as a weak base. So we find that usually a weak acid solution is acidic, and we find that a conjugate base of that weak acid, its solution is basic. And so the question becomes why? Well, we can illustrate that by using H2S Spider-Man and its conjugate base, HS minus Captain America. So we already know H2S Spider-Man is going to be able to donate a proton by shooting out the webbing, and then HS minus Captain America is going to be able to accept a proton by grabbing it from, again, shielding its impact and then using it for its advantage. Okay, folks, that's the way I think of it in my head. So if we start off by verifying a solution is acidic, we're going to start with our weak acid, H2S. We're going to mix it with water, and we're going to form H3O plus and HS minus. We can also call out the conjugate acid-base pair here, so H2S and HS minus. Now, guess what, folks? If you want to know why this solution is acidic, then we can use the strength of our conjugate acid-base pairs, just like we saw in the previous portions, and we see that the equilibrium is going to lie to the left. Okay? So that means equilibrium is going to lie to the left because this is weak and this is weak, and so our equilibrium is going to go towards the weaker area, right? That's what we saw before when we were just trying to figure out our net direction of these conjugate acid-base pairs. Always going to favor the weaker acid and base. And so because of that, that means we're going to have more of the H2S acid that we're going to be using, right? And so we're going to have more of the H3O plus that's going to be formed, thus causing the solution to be acidic. Now, what if we took the conjugate base, HS minus Captain America, and then took that conjugate base and mixed it with water? What would happen? When we take our conjugate base here and mix it with water, we're going to form H2S and also OH minus. And so the ability or the contribution of OH minus is coming from the HS minus here. We get a basic solution again because we're dealing with something that's weaker here versus stronger on this side. And so our equilibrium is going to move towards the left. That means we're going to have more HS minus Captain America, and that means we can have more OH minus in solution, and therefore we're dealing with a basic solution here, folks. And because it's a basic solution, then we can use that and mix it with water to, of course, get a Kb value. So this also would have its own Kb value here, just like this over here would have its own Ka value, right? So we have a Kb value here, and we have our Ka value. But what else? Sometimes you're not going to get both groups, right? You're not going to get a weak acid and then all of a sudden figure out its conjugate base and then mix it with water again. You would have to come up with that on your own. So of course, we're going to get into an example next as we go along, right? But I just want to let you know that you might not always see your conjugate base in the charged ion form. So if you're giving like NaF, for example, you would have to start layering information. So first you would say, okay, I'm in solution. So instead of NaF, this will be Na plus and F minus. Na plus we know is going to be spectator, but you have to ask yourself about this F minus. Is this F minus a conjugate base of a weak acid? Well, if you remember your weak acids, you know that a weak acid is actually HF. And when it's mixed with water and it breaks down to H plus and F minus. So that is a conjugate base of a weak acid. And so just because I was given this and I disassociated it into its individual ions and I was able to recognize that F minus was a conjugate base of the weak acid HF, then guess what, folks? I'm now able to then take my F minus, mix it with water, and create an equilibrium by forming HF again, plus OH minus. And if I have OH minus, I'm dealing with something that's basic. I can get my Kb value from here, and of course I can, fill out my Rice table, and that's how I would approach these type of questions. So again, sometimes you're already given the charge anion. Sometimes you have to disassociate what's given to, of course, get the charge anion. Okay, folks? So we want to keep that in mind as well. No matter what, this new understanding that the conjugate base can act as a weak base is going to help us with Rice table questions related to any anions of weak acids at that moment. How can we really go far and show a direct relationship between an acidic solution and a basic solution through their Ka values? Well, guess what, folks? Ka and Kb are both related to one another. And that's what's so awesome about it. Ka and Kb are related. So when they're related, it's when they're going to be coupled together. So we always have to go back to equilibrium. You're thinking, okay, when you have one or more reaction, they tend to couple with one another. And so let's say you have one K value, K1, and then you have another K value, K2. And when they couple together, you can end up getting an overall K value, right? We saw that in chapter 13. Guess what? We can apply the same here. we have a equilibrium constant for acid dissociation. We have an equilibrium constant K for base dissociation. When they're coupled together, we can end up getting an overall K value that then can relate these two values to one another. So how do we do that? We got to get our reactions to couple. So first, we're going to have our weak acid mixed in water to form H3O plus and A minus. It has its own Ka value, right? And that's going to be products divided by reactant. Next, we're going to have our base mixed with water, and it's going to form our conjugate weak acid and, of course, OH minus, and it's going to have its own Kb values. So what we can do is we can simply get rid of things that are the same on both sides, okay? So I'm like, okay, this is going to be a product and a reactant. I can get rid of that. This is a product and reactant. I can get rid of that. What's left over? 2H2O is going to form H3O plus and OH minus. Well, haven't we seen this before? Yes, we have. We saw this with the auto ionization of water, folks. And so because we saw this with the auto ionization of water, we know that this is also going to equal a Kw value, which is simply going to be H3O plus times OH minus. Okay? And if we know that we're getting our H3O plus from the acidic portion and we're getting our OH minus from our basic portion, we can then say our Kw is equal to Ka times our Kb value. And this is the relationship that we start seeing here. And we also know what Kw equals. Kw is going to equal 1.0 times 10 to the negative 14. So it all connects, folks. And so that means we have our Kw is equal to Ka times Kb. Therefore, our Ka times Kb is equal to 1.0 times 10 to the negative 14. So if I'm given a Ka value, can I find Kb? The answer is yes, because I can say my Kb is equal to my Kw value divided by my Ka value. Same thing if I want to solve for Ka. I can say my Ka is equal to my Kw value divided by my Kb value. So when I'm given a weak acid and I dissociate it, I can then use that value to help me find the Kb that I'm looking for example. And what else? If my Kw is equal to Ka times Kb, and this entire thing is equal to 1.0 times 10 to the negative 14, then I can use the p scale here to simplify it. So if I use the p scale, pKa plus pKb is equal to 14.00. Now I can choose any kind of relationship I want. I can use any interrelationship between pH, pKa, pKb, H3O plus, OH minus concentration. All of it now connects and layers, folks. So let's go ahead and get into an example. And remember, you can use this for any conjugate acid-base pair and any Bronsted-Lowry acid base at that point. And I also want to show you another way to get Kw, which is basically the same thing. It's just I want to use the expressions for Ka. So Ka is H3O plus times A minus divided by HA, multiplied by Kb, which is HA times OH minus divided by A minus. So again, you're able to get rid of the variables that are the same on each side, and you're just left with, on top and bottom, and so you're just left with H3O plus and OH minus, which we know is, again, the Kw value. So let's go ahead and get into an example. All right, we're back at the Avengers compound. Let's go ahead and read this question. Sodium acetate, CH3, COONA, represented by NaAC for this problem, is used in textile dyeing. What is the pH of a 0.25 molar NaAC at 25 degrees Celsius? They say the Ka of acetic acid is 1.8 times 10 to the negative 5. So when you're first reading this, you're like, okay, I'm given sodium acetate. So if I was to disassociate sodium acetate, which is what we have to do, all right, let's disassociate it. I have a CH3, COO minus, and I have Na plus, right? And so again, that charge negative here can represent a weak base. Why do I know that I'm dealing with a weak base of a weak acid or a conjugate base of a weak acid? Well, I've already read the problem, right? We already know we have to disassociate this. We know it's used in textiles. They want us to figure out the pH, and they already gave us this particular anion here. So again, they write it as NaAC. And so if we disassociate that, it'll be Na plus and then AC minus. So this whole thing here is going to just represent AC minus. That's all I did different. Okay? And they gave us the amount here. So we know if Na plus is spectator, that 0.25 is going to be the initial amount for this particular base. Then they gave us the Ka value of the weak acid itself. So they gave us the Ka value of acetic acid. And they said that's 1.8 times 10 to the negative 5. And so wait a minute, I have to ask myself, they gave me a weak acid Ka. They give me sodium acetate, which I know can disassociate into a conjugate base. Conjugate base of what, folks? The conjugate base of the weak acid that's given. So there's two reactions I like to write for my brain. First, I'm going to write the overall weak acid dissociation. So HAC plus water is going to dissociate to H3O plus AC minus, okay? And so this is how I'm now able to recognize that the AC minus over here is a conjugate base of a weak acid. So the next thing I'm going to do is take my AC minus and also mix that with water to form a basic solution. So I'm going to have HAC that's formed here plus OH minus. And this is where we are, folks. And this is exactly what you want to do when you run into these type of problems. Okay, folks? Now, I'm going to use this equation to help me solve for the OH minus concentration. And if I have the OH minus concentration, I can get the POH. If I have the POH, I can then get the pH like the question asks. But what else do we need to do, folks? We need to get the K expression. So here for this one, we have a Ka expression. But here we have a Kb expression because we're forming OH minus. So how do I actually get the value of my Kb? Well, I will use exactly the expression we had before. Kb is going to equal to my Kw divided by Ka. Another way to see this is Kw is equal to Kb times Ka. So all I'm doing is solving for Kb here. And so this is going to equal 1.0 times 10 to the negative 14 divided by what's given, 1.8 times 10 to the negative 5. And as you can see, I'm just going step by step. The first thing is balance equation and get the K values. We haven't even got to the right table step yet. So there's a lot to be able to consolidate and recognize with these type of questions so that you can actually answer them successfully, right? Okay, so I'm going to go ahead and get my Kb value. I divide these two numbers here and I get 5.6 times 10 to the negative 10. Therefore, I now have my reaction that shows the conjugate base acting as a weak base mixed with water, and I have the Kb value associated with it. I can then go further and complete my Rice table. Okay, folks? So again, this is showing the relationship between Kb and Ka so that we can then go further and use our anion of a weak acid to be able to finish and complete our question. So we're going to start by setting up our Rice table. We have our weak base here mixing with water that we got because it's the conjugate base of a weak acid. We're going to mix it with water and form the weak acid itself and OH minus. Our initial amount is 0.25. That's given. Our initial amount of the products are going to be 0. We're going to be getting rid of the reactant to form the product. So we have minus X and plus X here. And then finally for equilibrium, we have 0.25 minus X and then we have X and X. Now, because our Kb value that we calculated is 5.6 times 10 to the negative 10, we can effectively make an assumption here and get rid of minus X. So now it's going to be 5.6 times 10 to the negative 10, using our Kb value, is equal to X squared divided by 0.25. So I'm going to cross multiply 0.25 with 5.6 times 10 to the negative 10. I get 1.4 times 10 to the negative 10. I'm going to take the square root of both sides, and then when I do that, I get simply X is equal to 1.2 times 10 to the negative 5. And so that means this is going to be X and this is going to be X. I have effectively found my OH minus concentration. Now, instead of going further to use POH like I've done before, I'm going to take my OH minus concentration and solve directly for H3O plus concentration using Kw. So H3O plus is going to equal to Kw divided by my OH minus concentration. And remember, Kw is just equal to the H3O plus times the OH minus. So all I did was divide by OH minus to solve for the variable I'm looking for. So 1.0 times 10 to the negative 14, that's just something, yes, you will have to know as far as Kw, divided by 1.2 times 10 to the negative 5 is equal to 8.3 times 10 to the negative 10 molarity, and that is the concentration of H3O plus. Now, if we want to get the pH, like the question asked, we're just going to take the negative log of our H3O plus concentration, and we get a pH of 9.08. So this is how I approach these questions. Very similar to what we've already seen. To me, the beginning is the foundation. So if you can't get those equations and you can't figure out how to get the Kb value from a Ka or Ka value from a Kb, then it's going to be difficult to continue on doing the Rice table part, right? Because the Rice table part we got a lot of experience with thus far. But you have to know how to layer information and connect to it right when it's necessary.